Thank you, Kai. It's an honor to be here, to be honest. I knew HITS when we met for an astroinformatics meeting here. I think it was 2018, and I loved it. I think that HITS as an institution is like the perfect place to do research, and in a beautiful place such as Heidelberg. So I'm really happy to be here. I'll be here for a year. And so today it's my turn to give a talk. And so my talk is going to be mostly about machine learning plus astronomy. I do a lot of research on other fields. So I work also on satellite images, and I also work on biomedical images and genomics a bit. And but today I want to focus on what's my passion, which is astronomy. Okay, one of my many passions. Okay, so today I want to talk about how we apply machine learning to astronomy. And it sounds like, for example, if we want to classify, let's say, glasses, I grab the glass and I can classify it, and we apply some machine learning model, some vision transformer or whatever we want. And we are getting very good results with real data from the world, right? But astronomy is slightly different from any other field that we have been working on as a community. So first, astronomy is an observational science. And what I want to convince you is that during this talk is that this poses different new challenges that you don't see in other fields, okay? So we have massive amounts of data being produced every night, which everywhere in the world, this is happening, right? And a lot of machine learning have been applied to astronomy, and this is in bold font, because it has been just like directly applied to astronomy. And a lot of the machine learning that we have been seeing in astronomy does not take into account some major problems that we have in astronomy that we don't have in other problems around the world. So, for example, most of them do not take into account the observational processes that are unique to astronomy. I'm going to talk about this later. So we need to develop new machine learning tools to address these problems. It's not that we can get like out of the bookshelf a support vector machine and directly apply it. We have new challenges that we need to address and that we need to take care of. So I divided my talk into 4 chapters. I hope I will be able to get to the 4th one. If not, I'm gonna skip right through it. Okay, so chapter number 1, observational science. Chapter number 2, sequential data in a real world scenario. Chapter number 3, selection biases and domain shifts. Most likely you've heard about those terms. And chapter number 4, if we can really trust our predictions. So as an example of big data being produced, or that's going to be produced in a year from now, we have the LSST. So the LSST is the large, now I forget, the large survey of space and time. I think L is not for large. Okay, I don't remember. Legacy, sorry, yeah. Legacy. Legacy, that's it. Yeah, sorry about that. So it's a legacy survey of space and time. So basically, we as humanity have built this 8-meter telescope that's located in Chile. And it has a 3 billion pixel camera. It's one of the largest, maybe the largest camera in the world. And it has 3 mirrors, and it's going to produce around 30 terabytes of data per night. So what do we mean by that? Is that we're going to produce tonight, let's say one night, 30 terabytes of data. And the next night, we're going to have 30 more terabytes of data. And we need to analyze all this data so in a day, right? Because otherwise, it's going to get stuck one after the other, and we won't be able to work with it. How this is going to work? So this is a survey telescope. So the telescope itself, it's called the Vera C. Rubin Observatory. You can notice that on this slide, it says the telescope is going to see first light in 2019. So that didn't happen. And most likely first light is going to be next year. So that means that the telescope is going to be operating next year, 2025. So this telescope is going to produce this kind of images, and it's going to scan the sky every couple of nights, the whole sky, right? Around every 3 days. So we'll have like a movie of the sky, of the whole northern sky, southern sky, sorry. And what we're going to do is that it's going to pay particular attention to things that vary in time. So what type of things vary in time? for example, supernova, exploding stars, or asteroids that may potentially hit the Earth. So those are moving objects, right? So they vary in the sky. And the way this is going to work, and I'm going to talk a bit more about this later, is we're going to have a template image, and then we're going to have last night image, which is what we call the science image. And the template image is like a historic image from the past. And what you do is you subtract the image from last night. Sorry, you subtract the template from the image you got last night. And if something changes, you're going to see something like this, right? So this is like a small point there, right? And that means that this point was not on the template, but it was on the science image, right? So this is sort of the data we're going to get. Now, how much of this data we're going to get? We're expecting around 47 billion objects. So if you look at this image, you see a lot of objects. Each one of these points is like an object, right? And we're expecting to have 47 billion of those. And every night, we're expecting to have 10 million alerts. And an alert happens when something varies in the sky, right? So we need to address, this is like a large data problem, right? A massive data problem. Of course, you can compare it against Google and stuff like that, and maybe it's not that large, but for this particular case, we need to address the problem that this has to be analyzed in a day, right? 24 hours. So chapter number 1, astronomy as an observational science of things that are far, far away. Okay, so this is the first thing I want to make sure you kind of get into the problem here. These things that we're looking at, they're not here, right? And whatever we're looking at, it's like it happened like billions of years and millions of years ago, right? So let's say you have an image such as this. This is an image from Hubble. And you want to find things here, right? And say you find something like that. There's something there, right? And now you want to see what it is, okay? So if you have the very powerful telescope, you can go into it and see something like that, right? And you could see that this is a galaxy. It's a particular galaxy. And this is what we call a spiral galaxy or a disk galaxy. It has like a disk of stars that are moving around the center. And it has spiral arms. You can see those spiral arms, right? So this is one of the basic machine learning things that you want to do. You want to find objects, and then you want to classify them. So imagine we're not taking into account time right now, and we want to understand what that is, okay? If you're here in the real world, what we call real world, but in Earth, right? If I want to classify a glass of water, I can take it, I can pick it up, I can look around it, make sure that there's something behind it, right? If I look at my laptop, I don't know what's behind the laptop, but I can turn around, right? And I can look at what's behind the laptop. You cannot do that here with the Galaxy, right? And it's even worse because the only thing you get is a picture of it, right? You can get more stuff. You can get more data out of it. You can get a spectrum, or you can get a lot of different types of data. But in principle, you're getting light or a signal from something that's really far away, right? And you have to do the best you can to understand what that is, okay? So I'm going to talk about one of the basic things that you do with the galaxies. So let's say you have two types of galaxies, only two, right? One, it's what we call a disk galaxy or spiral galaxy, which has spiral arms. You can see those arms there, right? On the left image, right? Or you can have an elliptical galaxy, which is something like that. So those are stars that are in an ellipsoid, right? And they're not moving. They're like old stars usually. And they already processed all the material that they had to create new stars. So they're like maybe boring. I don't want to say that because if you're into elliptical galaxies, you may feel like. So let's say we want to do that, okay? So we're a team of researchers and we want to do something really simple, try to find those two different galaxies, those types of galaxies, okay? So Galaxy Suit, okay, wait. So this is data from the Hubble Space Telescope, but so this is a space telescope, right? It's in space. But you can also do that on Earth. So these are images from the Sloan Digital Sky Survey, and you can see that something happens, right? So apparently this images have much more detail, right? But these ones over here, they look kind of blurry. They look kind of blurry, right? So if you look from Earth, it's kind of a bit harder to classify them, but you can still do it, right? So Galaxy Zoo is a project that started maybe 2 decades ago. And the whole idea was to do crowdsourcing. So we have millions or thousands, hundreds of thousands of galaxies, and we show this to the whole human race, right? And everyone helps us classify them according to their shapes. So they have this classification tree. This is Galaxy Zoo 2 from 2013. And basically, the first question you ask is the galaxy simply smooth and rounded with no sign of a disk? So that's the first question. Then you can ask other questions like, for example, what the number of spiral arms, or if there's a bar in between, or if it looks like a circle or like a cigar or stuff like that, right? And so what they did they showed all this to the people, and these were the type of images that they were showing to the people. Okay, so this is like anyone could participate, not only experts. And you can see here that there's their classification. E is for elliptical, which means smooth with no sign of a disk. And S is for spiral, and which means that there's a disk, right? Can you see spiral arms around some of these? Some of these kind of, I'm not sure if you can see them, but some of them have the spiral arms there, right? But it's super hard to do this, right? Is it? So what we're going to do now is I'm going to focus on this particular task, okay? And we're going to do a crowdsourcing experiment with you guys, okay? So I stole this unashamedly on Alexei Ifros from the Heidelberg Laureate Forum. So I saw this and I said, oh, that's so cool. I wanted to put it into one of my talks. So this is the first time I tried. All right. So this was the question that was asked for the people. Is the galaxy simply smooth and rounded with no sign of a disk? And the answers could be, it's smooth, it has features or a disk, or it has a star, or it is a star or an artifact. So I'm going to get rid of this part. We're not going to do that. We're going to just classify them into smooth, features, or disk. Okay, so if you see, I'm going to show you images. If you see that there's a feature or a disk in the image, you just clap once, only once. All right. If it's a smooth galaxy, you don't clap. Okay. Okay, so in the previous example, you should have clapped for all of these. All right, and these ones over here, that you shouldn't have clapped for them. Okay, so if you think there's a disk or there are features like spiral arms, you clap. If not, you don't. Okay, are you ready? Yeah. All right. So first picture. Okay, that's easy, right? Second one. Okay, that's easy too. Third one. Okay, that's good, right? So thank you very much for participating in this experiment. So I just wanted to show you the last 6 galaxies I showed, okay? These are the last 6 galaxies I showed. Some of you clapped for some of them, some didn't, but we didn't agree, right? We weren't sure about them. Well, all of these galaxies were classified in Galaxy Zoo as not being a disk or not having features, spiral features. But if you go to Hubble, you can see you have better resolution for those images, and you can see that there are spiral features in all of them, right? Those are definitely disks, okay? So I kind of tricked you, sorry, but I wanted to prove a point. And the thing is that if we have bad data, our labels are gonna be bad, right? And if we train a machine learning model with bad labels, then our machine learning model is gonna learn how bad we're doing it as humans. So this is what we call observational bias. because we are biased regarding in terms of the observations we're performing. Okay, so message number one, astronomy is an observational science. Okay, we do not have access to the ground truth. We estimate it from observations, and our estimates may be biased due to the observational process. So what we did, the first thing we did, so we wrote a paper in 2014 and another one in 2018. We measured this observational bias. Okay, and we noticed, so we have here on the x-axis, 1, 2, 3, 4, 5, 6, 7 data sets, seven labeled data sets of the same galaxies. The first one is made by experts. Galaxy Zoo bias is the Galaxy Zoo labels from crowdsourcing. Galaxy Zoo D-bias is a method that they use to remove the bias from their labels. And HC11, it's from Huerta's company, 2011, which what they did was they trained a support vector machine. It's like a basic machine learning model on physical parameters over labeled, biased labels, okay? And on the y-axis, what I'm showing is the amount of bias that it's on each of those data sets. So experts have a very small amount of bias. Can you see that? Why? Because experts, they didn't just look at the image and say, yeah, okay, good, spiral. They looked really deep into them. They moved the color scales. They went and looked for other data if there was other data available and stuff like that, right? Then the crowdsourcing labels, they are super biased, but their method, their unbiasing method is able to remove that bias, right? But it's not as good as having experts, right? And then training a machine learning model, a very simple machine learning model with physical parameters over biased labels is able to remove the bias, okay? Can you see that? So what we did in 2014, we presented the framework, and in 2024, and now for the first time I noticed this is 10 years after that. So for my PhD thesis, that was 2014. What I did was I put I wrote like a methodological framework for modeling the observational process and to deal with machine learning models that are able to take that into account. And what I did was, so we have the real data that has a label, a real label that we are not able to get access to, right? But we assume that there exists a real label, okay? Like the ground truth that we'll never have access to it, but we're trying to estimate it. We get the data, and due to some observational parameters, alpha I, this label gets turned into something called yi hat, right? So that's the label that we as humans are estimating for this particular image, okay? And so what we did was, so what's in this alpha I, for example, the resolution of the image or the signal to noise ratio, stuff like that, stuff that biases us as observers. So what we did was something super simple. And what we did was we just wrote the likelihood dependent condition to these parameters, okay? And by minimizing this, we were able to de-bias the algorithm. In 2014, this was a logistic regression model, something very simple, but it's simple to try to address analytically. But in 2024, a student of mine, Esteban Medina, did deep learning on this, okay? So this is Esteban Medina, all right? And these galaxies I showed you were the ones that his algorithm was able to de-bias. And the most important thing was that he was able to train a neural network with biased labels and be able to remove the bias out of the model, right? So the model was able to remove the bias of the labels, and it turned into a unbiased model. So this was trained like every neural network, right? A loss function, we throw it in, a couple of convolutional layers, and that's it, right? But we modified the loss function. But the interesting thing is that I'm not showing it here, but the neural network was able to find what we call the Cersic profiles. Do you know what those are? If you don't, those are physical, it's a parametric model for the light of the galaxies. So the neural network found automatically, without us telling them, like physically relevant parameters, just by telling the model not to be biased. Okay. So, okay, so that was chapter number 1. Astronomy is an observational, an observational science. And so chapter number 2, sequential data in a real world scenario. So remember I told you about this? So you can get the template image and then the science image, and then you subtract them and get the difference image. All right, so we can do this. If we have a film of the sky, we can do this every night, right? So we can do it once, and then we can do it the next night, and the night after that, and so on and so forth, right? And then we can calculate the amount of light in each of these stamps, in each of these points. And what we do is we create what we call a light curve. So this is a time series of an astronomical source. So for the first point, we can get oh, there's a typo then. And so for the first point, we get the brightness. For the second night, we get the brightness, and so on and so forth. And we create what we call a light curve. And actually, a light curve looks something like this. This is a real light curve. Okay. So we currently are working on CDF. We're receiving around 100,000 to 1 million alerts per night, but we need this to scale up to around 10 million alerts per night, when the LSST will start operating. And so how is this going to work? I mean, if you have 10 million alerts per night, what is the community going to do with it, right? I mean, so this is the way that this is programmed to work. So you have the survey telescopes, and the data is going to what we call the community brokers. The community brokers receive all this data, they classify, they do a lot of things with it, and then they provide the data to the community and to follow-up resources. Okay. So in principle, if you think about this, you need what we call the community brokers here in the middle, so that you, as an astronomer, you don't get 10 million alerts per night, because you're not going to know what to do with them, right? So we created Alersi. I am the director of Alersi, and basically Alersi stands for Automatic Learning for the Rapid Classification of Events. This is one of the community brokers for the LSST. And it's also the name of a tree, which it's supposed to be the oldest living tree in the world. And it's a particular type of tree that that grows in Chile, where I come from. It also grows in Argentina, which is our neighbor country. And what is Alersi supposed to do? What are we aiming at doing? We're doing a lot of things here. I don't have time to go all over them, but you can see that there's classification, and we're calculating features for all the data we're getting, and we're creating outliers. We're looking for outliers and anomalies, things that we don't know as human race that they exist in space, right? So this is the kind of things that we want to address. And what type of sources we are trying to find were transient sources, things that last for a small amount of time or for a limited amount of times. Active galactic nuclei, these are stochastic sources. Variable stars, this could be periodic sources like one star around the other one. And solar system stuff such as asteroids. So this is the kind of light curves we're looking that we have in Alersi. The first one is the light curve of a supernova. So basically, there's a star that explodes, and then it starts diminishing its light again, okay? And this is an RR Lyrae, which is a periodic type of source. So it glows, and then it stops glowing, and then again, its brightness grows, and then it goes down, and so on and so forth, and it has a periodic behavior. So these are things that you can look at them, right? I was thinking about doing a similar experiment than the one before, but I decided not to because I didn't have time. But if you look at them, you immediately notice what they are, right? I mean, you can look at them and you say, well, yeah, this is growing fast, and then it's going slow, and then it's periodic, right? But in reality, data does not come like this. Data is something like that, okay? So how do we get from this to understand what is really happening behind that particular? You can see that there are some obvious things happening here, right? Like, for example, there's a lot of time here where we don't get data, right? So here on the x-axis is time, right? And because the Earth is turning around the sun, right? Sometimes we just cannot look at some particular objects, okay? And there are other things that happen that are not related to astronomy itself, but to human decisions, such as this. So this is a particular source. I want to pay particular attention here to that part over there. I'm gonna zoom in. Do you see something weird here? Is there something weird there? Right, so you can see that. Can you see that part over there? You know what was that? So we were processing the data, and we had our machine learning models running on the data, and we were receiving alerts. And at some point, the telescope or the team of scientists that run the telescope decided that for 2 nights, they were gonna do like really fast cadence, and they didn't tell us. So we were receiving like 1 or 2 points every week, and suddenly one night we received like 100 points. And the next night we received another 100 points. So it was crazy for us. We didn't understood what happened, and then we called them and said, yeah, we decided to make this, right? And yeah, but you know how this affects the machine learning models? I'm going to tell you about that. So we have, I'm going to talk very briefly about this. So we have a random forest that's currently working on the CDF data. So Alerci is already connected to CDF, and we have a random forest model. We calculate around 175 features, and we used a balanced hierarchical random forest, and we classify this as the confusion matrix. What I want to pay attention here is that we do classification into 3 like broad classes: transient, stochastic, and periodic. And then that's the hierarchical part. We classify into subclasses. Okay. So we have a random forest, and it's like our star model from 2021, and it's still running and it still works. And how do we do this? Well, we usually have a lot of models that we have been training, and we start by doing research on some particular model. Then this goes into development. So if a particular machine learning model works, this is like a very complex system, right? So Ignacio Reyes is the lead engineer of the project. And so we hand in the model to him and his team, and they would go and put the model into what we call, they will test the model, right, into the system. And what happens after that is that it goes into staging. So this is like one step before going into production. And that goes through quality assurance. So we have a quality assurance team led by Alejandra Muñoz, and they make sure that everything that's going on through the alerts, everything is classified correctly, and that everything makes sense, right? And basically, she does different types of plots, and they make sure that what the system is classifying makes sense, right? And after that, it goes into production. But until early this year, we only had in production the random forest model, right? Even though we have tried like maybe 10 or 20 models. Why? Because it hasn't passed this quality assurance part. They don't. So an example of this is the anomaly detector. So now this year, we're finally putting into production the anomaly detector. This particular project was, so the whole idea was, let's look for things that we don't know they exist, right? Things that they are there and no one knows that they exist, right? So Manuel Perez Carrasco, he's a former student of mine. And what he did was he created a model. He said, okay, I will test a whole bunch of models, but I'm going to build my own model. And his own model was something like this. And it's basically a neural network that grabs the data and turns the data into a latent space where objects from the same class should cluster together. That was the whole idea. And if something is not part of your labeled data, then it would look as an outlier there in the latent space. And so he tried a lot of algorithms. So 1, 2, 3, 4, 5, 6 algorithms. Okay. And here what's showing this is each column is he hit one class. So he hit, for example, here the superluminous supernova on this column, and he hit the supernova type 2 here on this column, and so on and so forth. And he trained different models for each of these data sets. So he was trying to see if the outlier detection algorithm was able to find the hidden label, right? And so basically what he found out here is that his model was very good, and that's it, right? But so this took Manuel maybe 6 months, all right, to do this plot, but then it had to go into production, right? But before going to production, we needed to test how the model was going to perform on real data. And this is what we have, what we found. So on the x-axis, you see the number of candidates ranked according to their anomaly score. So so 0 means that it's the most anomalous according to the algorithm. And you can see that the real outliers are in blue. The wrong class, it's like something that should have been classified as, let's say, a supernova, but it was classified as AGN or something, right? Are on orange, and in green, it's like nothing special. It's like not really an anomaly. And you can see that the proportion of objects, so you can see that he found, you have 40 here, right? He found 1, 2, 3, 4, okay? How do you do this? Can you think of a way of doing this? How to make sure that on unlabeled data, you're getting real anomalous objects? Something that you don't know it exists, right? Can you think about how to do that? I'll tell you how we did it and why it took 2 years to do this. We gathered a team of 12 astronomers to look at each of these objects and to agree on that those were really anomalous sources. So it was really hard. So we had 12 astronomers discussing all the objects that were found by the anomaly detection algorithm. And you can see that even though here it looks in the numbers that the model was really good, in real life, in real world scenario, it wasn't like that, right? Basically because the algorithms never performed the same on the real data than on the training data. Okay, so this is part of chapter number 3, which I'm going to talk about now. So this is a plot that shows the number of papers in astronomy that mention deep learning. Okay, and you can see that there has been a lot of them growing up since I would say 2018, 2019. Okay, so lots of deep learning models. But as I told you, in Alerce, we only have a random forest running. So why? If so many people have been publishing deep learning algorithms, why? So the question is, the answer is, we tried a lot of them. This is an experiment we run, I think in 2020. We ran all the deep learning methods that were available at that time for the real alert stream, and they didn't perform correctly. They didn't perform well. So you can see here that the random forest outperforms all the other models, okay? Why? Why can that happen? So this is message number 2. Machine learning models should work on real unlabeled astronomical data, okay? So what happened is that those particular models were trained either on simulations, and they were tested on simulations, or they were trained on a particular type of supernova, and then they were tested on that particular type of supernova, okay? So machine learning models need to take into account the distribution of the real data, and training on simulations is not sufficient, and testing on labeled sets is not sufficient. So we need to find ways of testing our algorithms on data that is not labeled, on real data, the data that we're going to get from these really fancy telescopes. So that was what happened in Alerce until we developed this new model, which is called ATAT, Astronomical Transformer for Time Series and Tabular Data. So this is a transformer model. I'm not sure if you know, you're familiar with what a transformer model is, but it's basically a particular deep learning architecture. So this was the idea of a former student, Nicolás Astorga, and Daniel Moreno helped him develop this. And basically, it's a transformer model that has two processing lines. One is for the light curve, and the other one is for the features. So he built a feature transformer that would create a representation of the features, and we also have the representation of a light curve, and then they get concatenated, and then you run deep learning standard multi-layer perceptron on top of that. Okay, so these are the two models that that will be put into production hopefully during the next weeks. And you can see that we also added new classes. So our anomaly detector helped us find sources or classes that we weren't considering before. So we added them into, so for example, microlenses, they were not part of our taxonomy. And we found a lot of microlenses on the anomaly detector. So we added them as part of our label data. Remember I told you about the change of cadence? Well, Daniel Moreno with Alejandra started working on this, like what are we gonna do when the cadence change? So the cadence is like the number of observations you're performing per night, okay? That's the main idea. So this is super important because so right now I would say the cadence for the LSST is not yet defined. So that means that we will know the cadence when the LSST starts operating. And most likely, and I can sign that for you, they are going to change the cadence while they're running the survey. So at some point, they're going to say, okay, well, let's do something different, right? Let's modify the cadence. Let's observe more points per night, right? So what they did was, so you can see here on the blue line is what happens to the model. Okay, so on the x-axis first. The x-axis here is the date where the high cadence experiment happened, the first one, and this is the date where the second one happened, okay? So this is no high cadence before that, and in between no high cadence. And what they found out was that if you use on your transformer model, you input the light curve for 5.8 years, then there is no difference, right? The performance, it doesn't impact the model as bad. But if you're only using a month, then it impacts the performance, okay? So basically, but I have to say, so this was an experiment we ran this year, but we already knew about this because Daniel, for his master's thesis, he worked on this. So he worked on what happened to the transformer models if you change the cadence. Okay, so he ran an experiment. He created 1, 2, 3, 4, 5, 6, 7 transformer models, different types of attention mechanisms. And he tested all of them with macho data. So this is another survey. And so here, macho full means with a whole light curve. And then he removed a fourth of the points, then a half of the points, and then 3/4 of the points. And then he changed dramatically to another survey, to other 2 surveys with different cadence and different magnitude limits. So basically what he found, one of the most important things he found is that you need to concatenate everything in the center of the transformer model. So the position encoding should be concatenated to the representation of the light curve. If you know what a transformer is, this may make sense to you, but basically you have a vector that represents the position of the data, and you have a vector that represents, let's say, the flux, the brightness, and you have to concatenate them instead of adding them up, which is the standard way of doing it. But he also created something that's called P, which means position I don't remember, positional encoding on attention. So what he did was, after the attention mechanism, he put the positional encoding back in. And that worked when the not only the cadence, but also the brightness distribution changes. So message number 3, survey telescopes may, and most likely will, change their cadences unexpectedly. So that means that we need to train models that need to be robust enough to deal with sudden changes in the data distribution. And this is something that you usually don't do in life, right? I mean, if you think about an image detector, your camera trying to find faces, you don't suddenly switch the distribution of the faces, right? But this is something that's happening in astronomy. The distribution of the data just changes because it happens, because humans, right? We decide to make some change. We decide to look faster for things, stuff like that. I'm going to briefly talk about this because I'm running out of time. But chapter number 4 is, can we trust our prediction? So I would expect that if at some point the cadence changes and the model stops working, the model should tell me I'm not sure what's going on here, right? Instead of me as a human saying, well, something's wrong here, right? So this falls into the field of calibration and uncertainty estimation. So this is a work that's being done by a current student, Martina Kais. And basically what she did is she worked with Astronomy, which is a foundation model that we created maybe 2 or 3 years ago. And she turned it into an uncertainty estimation, or she put it inside an uncertainty estimation method framework. And so basically, you have here different types of uncertainty estimation methods. And she proposed her own. This was totally her idea. I didn't tell her exactly what to do. And but she also created this, which is, I can try to explain briefly, but basically, you create the representation of the data, so you have a vector of that representation, and you put another layer on top of that that projects that representation, that's a vector for each object, right? Projects that representation into what we call prototypes. So we have different prototypes, and you project those onto the prototypes. And then what she does is that she puts a layer on a Monte Carlo dropout, which is basically activating dropout when you are doing the inference. So by doing that, she was able to do much better than all the methods that she tried from the literature. Okay, so I'm almost done. So final takeaways. Well, the first thing is that astronomy is an observational science, right? So there are massive amounts of data being produced every night. And machine learning tools, again, have been applied to astronomy during the last decades. A lot of them have been applied directly, but so the community usually grabs the machine learning tool and applies it directly, right? But that's not the way we should be thinking about this. Machine learning is a totally different field. It's a totally different animal, and we should address it. I mean, astronomy is a totally different animal, and we should address its machine learning challenges in a different way. We need new machine learning models for astronomical images or for astronomical data, right? And this should consider bias labels, domain shifts, and in particular, this is something I didn't talk about, but multi-messenger astronomy is basically that we're receiving different types of signals from the universe. So we talked mostly about light right now, right? But they're like gravitational waves, for example. We need to, and sometimes you have 2 or 3 or 4 instruments that are looking at different frequencies in the sky at the same position in the sky. And then you should be able to grab all that data that comes from totally different distributions and being able to input them into your machine learning models. And that's it. Thank you very much, and I'm happy to take questions.